So there's a lot of information they give before they ever start getting to examples. But a function is a solution of a differential equation if it satisfies the y and its derivatives are replaced by f of x. We all know what solution is. We've been talking about solutions since like algebra 1. It's a solution if it makes the function work. We've looked at general solutions where you like a plus c or something like that. And then we have specific or particular solutions, which we have done as well. And so they start introducing this idea of plugging functions in for functions. The first example here is just verifying a solution. Does this work for the information they're giving us? Determine whether the given function is a solution of the differential equation y double prime. So this is second derivative of y minus y equals 0. So what they're saying is, if you take the second derivative, you actually end up with your original function, because if you subtract two things that are the same, you'll get 0. So they want to know if any of these satisfy that particular differential equation. So the first one, sine. So what we're going to do is we're going to take the second derivative here. What's the first derivative of sine?
Cosine.
Just cosine. What's the second derivative then? So derivative of cosine? Negative sine. So what they're saying is, does the second derivative, negative sine of x, minus the original sine of x equals 0? No, that's going to be negative 2 sine of x. It does not equal 0, so it is not a solution. That's all they're asking right here. All right, let's look at the next one. Y equals 4e to the negative x, all right? First derivative of that guy. Remember, it's just going to be your function that they gave you, and then the derivative of your exponent. What's the derivative of negative x? Negative 1. And then the second derivative, what they gave us, right? And then the derivative of the exponent, so times negative 1 again. So my second derivative is just 4e to the negative x. What's going to happen here? Yes. This is true. This is a solution. And then the last one. First derivative, that c is just a constant. Well, it's just going to be the function. Derivative of x is just 1. If I do second derivative, I get the same thing. So this one's also going to work. That is also a solution. All right. So they're just trying to figure out, does it work for what I've given you? That's what they're asking here. Does it work for what I've given you? Geometrically, so thinking about what the picture of the graph is, the general solution of the first order differential equation represents a family of curves known as solution curves. We've talked about this before. A general solution is a set of answers. That plus c will change it. Think of it just with linear graphs, right? Y equals mx plus b. You can have an infinite number of lines with the same slope, right? Where it hits the y-axis determines which specific line it is. But if you just had y equals 3x plus c, that does not narrow it down to a specific line. It narrows it down to a set of lines that fall on the coordinate plane with a specific slope. And so that's what happens here. For every value assigned to the constant, you get a new function. And they've given you one here, y equals c over x. And they give you the graph there of y equals c over x. Your 1 over x graph. It could be positive, negative, like it really flips around the graph there. What we start seeing way back in chapter 4 was particular solutions. And so that's where we look at particular solutions here. And what happens with particular solutions is they give you this thing called initial condition. And that initial condition leads you to what c actually equals, and then you have your answer. In linear equations, it would be something like point slope. You have the slope, and then they give you some random point on the line, and now you can figure out what the exact y equals mx plus b is because you've given some information to help you track it. They use your acceleration here as an example. And so you'll remember when we did acceleration problems, acceleration of negative 32 you took the antiderivative and you got this negative 16t squared plus some constant c, or you got negative 32. Where'd they start? They didn't show me that one. You got first derivative of like negative 32t plus some c. And then you took the antiderivative again, and you got negative 16t squared plus a constant times that t plus some other constant. This is a general solution. And then all of a sudden when they start giving you initial conditions, oh, well, the initial position is 80, the initial velocity is 64, then all of a sudden you have a particular solution to this problem that we originally had. And so that's what we've done so far with this. And so what we're going to start doing is we're going to start doing that, but we're going to start doing it with two variables, with y and x. And you'll see that is where we start to do what's called separation of variables. So the first thing we're going to do is find a particular solution. All right, so it says, for the differential equation x, y prime minus 3y equals 0, verify that y equals cx cubed is a solution. And then find the particular solution determined by the initial condition of y equals 2 and x equals negative 3. So they've given us this function here, x times y prime minus 3y equals 0. And the first thing what they want us to do is they want us to just say, okay, make sure that this is a solution. So if I plug that in for y, is it a solution? Now you'll notice y prime is in my original equation there, so I have to find y prime. Well, y prime is going to equal the derivative of this. Derivative of cx cubed. What's the derivative of cx cubed? I take that 3 and I put it in front, right? 3 times whatever that constant is, x squared. That's my derivative, right? And so now I'm going to plug in my y prime and my y into my original to see if it works. So I'm going to say x times my y prime, 3cx squared, minus 3 times my original, cx cubed. Does that equal 0? Well, if I were to multiply this, I get 3cx cubed minus multiply this, 3cx cubed equals 0. Yes, that is definitely a solution to it. So it's a solution. And then they want the particular solution. So this is a general solution. It has a c in it. They want a particular solution. And they have given me some parameters for that particular solution, an initial condition here. They've given me a condition when y is 2, x equals negative 3. So all I'm going to do is I'm going to take this and I'm going to plug those in for it. So I'm going to say when y is 2, x is negative 3. Y equals c x cubed. Y equals c x cubed. Negative 3 cubed is negative 27. So 2 equals negative 27 times c. So c is going to equal negative 2 over 27. So to make this a particular solution, then we have a general solution up here. A particular solution would look like this. Y equals, instead of c, I'll write negative 2 over 27 x cubed. Or you can put the x on top. They are the same. Particular solution. Separation of variables, page 371. Consider a differential equation can be written in the form m of x plus n of y dy dx equals 0. So in this case, we have a function of y and a function of x in the same problem. dy dx is just y prime, right? It's just the derivative. And so when you have this, what you must do at this point is get your y with your dy and your x with your dx. And we talked a little bit about that in one of the examples before. If you look down here at these equations, these examples they give us, x squared plus 3y, there's two functions, x squared and 3y. And then we have this dy dx here, that's y prime. So we have been doing equations up to this in this section with y prime and y in the same thing. That's basically what they're doing. And say that equals 0. Your goal here then is to get the 3y with the dy and the x squared with the dx. So what they did here is they moved the x squared over, and then they multiplied by that dx. So now we have 3y dy equals negative x squared dx. So now we could actually take the antiderivative of both sides here, which is what this dx indicates if you're trying to solve this. And you can actually integrate both sides at this point. Here we have sine of x, y prime, cosine of x. Well, y prime can be written dy dx. Multiply both sides by the dx, you will get, and then they did, this is sine of x, so then they divided by the cosine. They divided the cosine by sine, so we divided this, and then we have dy dx equals cosine over sine, which is cotangent, and then we multiplied both sides by dx. So this is basically what separation of variables is. They did the same thing here, x and y prime, e to the y. They made this a dy dx, they divided by x and multiplied by dx. And we get this. So this is what separation of variables means. Separate the variables with their respective dy or dx. All right? Find the general solution. Look at example 3. General solution. So this is going to have a plus c. We are integrating here. Integrating, not doing derivatives. X squared plus 4 dy dx equals xy. All right? And so for this one, we need to get the y over with the dx, and we need to get the x's with the with the dy and the x with the dx. Now, I will tell you, if the dx is on bottom, he's going to have to be multiplied to the other side. So it kind of tells you what side you're going to have to put these on. The y is going to have to be on the left, the x's are going to have to be on the right. Because you don't want the dx in the denominator. That's not what you want. It's got to be out of the denominator. And so even if you do that first, so you can see where you're headed, if I multiply both sides by this dx here, you'll see that I have x squared plus 4 dy equals xy dx. And so now I need to get this guy over here and the y over there. So if I divide both sides by x squared plus 4, I have dy equals my x, I'm going to write it this way, over x squared plus 4 dx. And this is being multiplied by this y, right? Just putting it there so you can see it. So then I have to divide both sides by y. There is a 1 here, so I have 1 over y dy equals x over x squared plus 4 dx, all right? Now, at this point, I can actually do my integration. So at this point, I can do the integration here and the integration here. Now you have to use all your integration rules that you know. On the left-hand side, when I have 1 over something, the antiderivative of that is going to be natural log. So on the left-hand side, I'm going to get natural log of the absolute value of y. On the right-hand side, I'm going to have to really think about u substitution. My denominator here would be my u substitution. I have x squared plus 4, and then I have an x on top, right? X on top. And so basically, if I were to do this as my u, x squared plus 4, right? My du would be 2x. I don't need a 2x, I need an x, so I'm just going to have that 1/2, right? So on the left-hand side, I'm going to have 1/2 times the natural log of my x squared plus 4, right, plus c. And I can, basically what they did here is they just condensed, okay? So that 1/2 can go where? Where can I put this 1/2 if I have a natural log? When it's, yeah, it goes in the exponent. So I will have the natural log of y equals the natural log, and that's where we get the square root of x squared plus 4, because that's to the 1/2 plus c. Now I am trying to solve for y. I do not have y by itself right now. What do I need to get rid of to get y by itself? The natural log, right? How do I get rid of a natural log? What gets rid of that base, natural log? E. So I'm going to say e on both sides. And what happens is the e cancels out the natural log. The e cancels out the natural log. All right. I have the absolute value of y. How do I get rid of absolute value of y? What do I have to consider on the other side if it's absolute value? Yeah, so I can basically just say, oh, well, the positive and negative on this side, right? And I need a little guy right here. We didn't condense. We need to condense. I thought it right here. We also need to do E right here as well because it's a plus C. We have a little E there too. Plus or minus, we need to consider the plus or minus over here of the square root of x squared plus 4, right? And we need to consider the e to the c, which is what they have there. All right. And that will get my y by itself. And they condensed actually further, but you don't have to. It's fine.